Hello there, hello everybody, and welcome to a new open class. Welcome to open class number 192. And today we are going to see how to combine different ROS2 concepts, some of them that we have seen in previous classes, some of them which are relatively new. So how to combine all these in order to create an automated warehouse system with ROS2. All right, so this is going to be the goal for today's class. It's going to be great. I hope that you enjoy it and you get lots of fun. And yeah, so let's not lose any more time and let's already get started. Let me switch here to my computer screen so that I can start seeing all your messages and everything. Let me go for that. There we go. 1 second. I think this is not capturing. 1 second. There we go. Okay. There we go. All right. So, yep. Let me go to the live class so that I can get your messages. Hello, everybody. Okay, many messages already here. Even before the class started, I can see some new names, maybe. So, is any of you new to these open classes? Is this your first open class? If I may ask, some other names are already familiar, like Gilbert. Constantino says that it's his first class. Also, Fayez. Gilbert says that he is new, but I know he is not. First, okay, so many people, it's their first open class. Okay, very interesting. All right, so this is very good right now because I wanted to share something with all of you, and let me do it right now. I'm going to share a very quick form here in the chat so that you guys can have a look. Basically, because I am interested in how did you learn about the open class, right? Because I can see many new people today, so I'm kind of curious to how did you know about this open class and why you decided to start with the class today. All right, a mail announcement says Fayed. Okay, so I have shared this form which has these questions and some others. So yeah, please. It just takes email, newsletter, LinkedIn. Okay. All right, then yeah. So let's already get started. Just take a few moments to answer the form whenever you have a moment. And yeah, let's go for it. So welcome everybody. Welcome to this open class. I hope that you are going to enjoy it. Now, the very first thing that you have to do before starting with the open class itself is to get a copy of the project for today's class. All right? So every class has a project associated to the class. And what is a project? You might be asking if you are new here. Well, a project basically it's a ROS project, a self-contained ROS project that can be shared easily with any users. In this case, I am sharing this project with all of you. Okay? Why? Because this project is going to allow you to practice, to work and to practice with robots while we are doing the class. All right, this is super important. This class, Gilbert and Sashat say, I cannot fill in the form. Okay, why is that? Permission issues. Okay, let me see if I can fix it. Okay, all right. Okay, you need permission. Yeah, I have already told my colleagues, so hopefully it's going to be fixed in the following minutes, okay? Then, as I was saying, these classes are not meant for you to be just sitting in your computers and listening and watching to what I am going to be doing, okay? These classes are focused, very focused in practice, okay? So I want all of you to be practicing with me while we are doing the class, okay? So that is the goal. That is why I am sharing the ROSject with all of you. Then how can you get this ROSject? Very easily. All you have to do is to click here in this button that you have right above the chat here, which says fork and open the class ROSject, okay? So everybody, let's go and click on this button. I'm going to click also here myself. There we go. All right. Okay. Then when you click on that button, a couple of things are going to happen. Okay. First of all, you are going to be redirected to the main ROSject page, which is this one I am here right now, with the streaming panel here in the right side, with the chat, the video feed. Right. I'm going to remove this from here and actually open it in another tab, so that I can have the chat. But you can leave it here. You can organize the main ROSject page as you prefer, all right? Then let me put it here for me so that I have the chat here. And then this is the main ROSject page. As you can see, it's loading. It might take, I don't know, maybe up to 1 minute to fully load. And when it finishes loading, you are going to see the ROSject page, okay? Now, meanwhile, this loads, let me tell you about another thing. So, besides this, a copy of this ROSject has been created, has been added to your account, okay? So, how to access this copy of the ROSject is very easy. You have to go here to the, in the left menu, you go to the My ROSjects section, here inside Develop, My ROSject, okay? And then here you are going to find a copy of this ROSject, okay? And this copy is already yours, okay? So you can come back and access this ROSject tomorrow, next week, next month, whenever you want, okay? So this copy of the ROSject is already yours forever. Then let's go back. Let's go out to our ROSject. Okay, so once the ROSject finishes loading, you are going to see something like this. Very important, you are going to have here the notebook, yeah? This is the notebook for today's class, where you are going to find all the instructions, explanations, sample codes, commands to execute, everything, you are going to find it here, okay? So very important to, in order to follow the class properly, okay? Yeah? Are we good? Has everybody opened the ROSject properly? Is everybody here with the notebook opened and everything ready to get started? Any issues so far? Yes, perfect, all good, ready for takeoff. Okay, awesome, awesome. All right, then let's get started, okay? So, yeah, as I was saying, today we are in the ROS Developers Open Class 192. We are getting really close to the 200 mark. It's going to be very soon. And in the last classes, by the way, as we have many new people, let me just tell you that you can access the previous open classes here in the self-led courses in the section open classes, okay? If you come here to the open classes section, here you are going to have access to all the previous open classes, okay? Also in our YouTube channel, you have them all available, all right? But yeah, so why I am saying this? Because today we are going to be working still with the BotBox, which we have been working in the latest classes, as you can see. And we are going to be combining some topics that we have reviewed in previous classes, specifically in the perception section, that we have been doing some classes with perception. So we are going to be reviewing a perception topic and combining it with other skills in order to create an automated task for our warehouse, okay? And for this class, as I was saying, we are going to be working on the BoxBot, okay? Which is this super cool environment that I have been introducing lately. In fact, give me just a second, because I'm going to show to all of you the BotBox video so that you can have a quick overview of it. So let me put it right here, right now. So this BotBox, this is for all the new users so that you know what I am talking about and what we are going to be using today. This BotBox is a portable robotics lab designed to help teach robotics in general and ROS more in particular. And with BotBox, you will be able to deliver experience-based robotics classes with minimal preparation and maintenance. This BotBox includes everything you need to make your students learn and practice about programming robots, such as a set of wheeled robots equipped with a LiDAR laser, camera, and a gripper, which we are going to be using today, also the gripper. It includes a small warehouse environment, which you are seeing right now here, a simulation of the whole system. It also includes a set of ROS2 projects already prepared for you, and many more things. So basically, this BotBox makes robotics education more accessible, allowing teachers to deliver practical robotics classes without any special preparation. Everything is already prepared for you. All right? And you can make your students or even yourself practice with topics such as robot perception, robot navigation, object detection and grasping, and many more. All right? Then I have also shared, let me stop it here. I have also shared here in the notebook at the beginning a web page that you can click in case that you are interested in learning more about this BotBox. All right? So today we are going to be using this environment in order to teach about warehouse automation. All right? And how are we going to do this? Well, we are going to do this by starting a simulation, a gazebo simulation, like the one that you can see down here. Okay? This is a simplified version of the simulation that is included in the BotBox set, by the way, okay, which is much more detailed. But we can use a simplified version because it's enough for this class. So let's actually get started and let's launch the BoxBox simulation here. And we can do this by executing the following command that you can find here in the notebook, yeah? In the launch the simulation section. Now, in order to be able to execute a command, you need a terminal, right? A shell. Then, in order to start a shell, what you have to do is to come here to the down menu, to the below menu that you have here with the icons, and click on the first one that you will find here, which says Web Shell. If you click here, this is going to open a new empty terminal, okay? This is just a regular Linux terminal, all right? Now, in this terminal, you can type commands, right? And in this case, we are going to execute the following command, yeah? So my suggestion is that you just select the command here from the notebook, copy it, yeah? You copy the command from the notebook and you paste it directly here into the terminal, yeah? Just to speed things up, all right? Then here you can directly execute the ROS2 launch command and the gazebo simulation is going to get automatically started. You can see here after some seconds, a gazebo window is going to pop up and we should be able to see the simulation here, all right? Yeah? Here we can see the environment with the BotBox. Yeah. So far, so good. Has everybody been able to launch the simulation? Okay, I can see Ricardo has said here that the questionnaire permissions issue has been solved. So you should be able to fill it now without any issues. The open gripper action does not finalize. Okay. We'll get there in a moment, Gilbert. Let me make sure that everybody has been able to launch the simulation. Everything good? Yes, 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 yes. Okay. Okay, so everybody has been able to launch the simulation. So far, so good. Then we are ready to keep going. Now, if you have a look at today's simulation, you might find something new which wasn't there in the previous classes. It's this gripper system, okay? This is a simplified representation of the actual gripper that is available, that comes with the BotBox, okay? Here you can see some images of the real gripper that comes with the BotBox, okay? And here we have a simplified version of this, but basically this acts as a gripper. So you can use it to pick up things, okay? Yeah? Then, how to operate this gripper? Here, you have a couple of commands in order to close and open the gripper. So let's test them real quick, okay? Now, in order to execute more commands, you are going to need more shells, more terminals, right? Then don't worry, it's very easy to open more terminals. You just have to click here in the plus button in order to create a new terminal. Yeah, I'm going to click here myself, and there you go, yeah? It's important that you don't close or anything or terminate the first terminal, because here is where the simulation is running. So if you close this one, the simulation is going to stop working. All right? Then we are going to leave the first one open, and we are going to create a second terminal here. Yeah? And then here we are going to be able to test our gripper. Let's see. Let's copy the first command, which should allow us to close the gripper, as it's indicated here in the notebook. So let me try this. Okay. And we can see that the gripper fingers have closed. Yeah, here. Now let's test the second command very quickly here, which is down below. Let me put here the simulation so that we can see it live. And now we should see how the fingers open. There you go. Okay, so this one is not terminating for some reason. So maybe this is what Gilbert was saying. Okay, no worries. Just manually stop it with Control-C, and that's it. Okay? Yeah? So far, so good. Is everybody able to open and close the gripper? Yes, yes, yes. Okay, very important, because we are going to be using this gripper later in the class. Okay? Actions work fine. All right. Excellent. Is everybody familiar with ROS actions? Because I can see that Stefan is already mentioning this, but we are here working with an action, as you can see from the ROS to action here keyword. So this gripper controller is an action server. Okay? Is everybody familiar with actions? I suppose that some of you are. BBM, for instance, he is not familiar with actions. Okay? Okay, so I'm going to talk a little bit more about actions later. Okay? So stay here, because later I'm going to talk a little bit more about actions, and I'm going to share a link so that you can learn more about actions. Okay? So just stay here in the class with me. All right. Then we are able to control our gripper, so let's keep advancing. Now, okay. So with all the proper introductions being made, let's go to the goal for today's class, for today's mission. Let me drink a little bit. So the goal for today's mission is going to be to transport the goods. Yeah? What are the goods? The goods in our case are these cubes that you can see here at the sides of the robot. You can see one here, you can see another one here. Yeah? And these cubes represent boxes that are in the warehouse, okay? And in this case, as you can see, these cubes are marked with what is known as an Aruco marker, okay? These black and white patterns that you can see here, these are known as Aruco markers, okay? This looks very familiar to something that we worked with a couple of classes ago, if you remember, yeah? Where we made a class on perception with April tags for ROS2, right? So this is very similar to this. If you attended this class, you know what I am talking about, yeah? So these are Aruco markers, which basically it's the same idea of April tags. All right? Then our goal is going to be able to transport, well, not transport, it's going to be to detect, to autonomously detect this box, pick it with the gripper, and transport it to the unloading section of the warehouse, which is, let's say, in this corner here of the warehouse. Yeah? So this is the goal of this open class, to be able to detect, go to the position of the cube, pick it up, and place it, move it to a different place on the warehouse. Yeah? So this is a fully automated task based on this warehouse environment. Okay? So this is going to be the goal for today's class. Is it clear? Bruce says, waiting for an action server to become available. Are you having any issue, Bruce? Let me know here if you are having some problem. Okay. Then, the very first thing, if we divide all our tasks in different parts, the part one would be to be able to detect the pallet cube. Yeah? So we need to create some kind of program that allows the robot to detect this pallet cube. Okay? So this is what we are going to start doing. Then let's go for it all together, okay? The very first thing that I'm going to do is to create a new ROS2 package where I'm going to place all the programs that I'm going to be creating, okay? So let's go ahead and let's create our new ROS2 package. So the very first thing is to go inside the ROS2 workspace SRC folder so that we can create our package here. And then down here we have the full command to create the new ROS2 package. Yeah, ROS2 package create, etc., etc. Here we go. Then if we execute this command here, we are going to see that we have created this new package, pick and place, okay? Which is alongside this ROS2 underscore Aruco package. This package was already there, yeah? It was already inside the project, but this one, we have just created it with this command. Yeah, ROS2 package create, pick and place. Now, at this point, I'm going to recommend all of you to open the code editor, the graphical code editor. Yeah, because it's going to be easier to create, edit programs, and so on. So let's go again here to the bottom menu, and this time let's click on the second icon, which says Code Editor. Let's click here, there we go, and this is going to open here a graphical code editor, okay? Like this. This basically it's going to allow you to navigate through the ROSject files with a graphical environment, which is always much more convenient, right? In this case, we are working with the ROS2 workspace, and if you go inside the SRC folder, you are going to find the ROS2 Arbuco package that I'm going to talk about it later, and this pick and place package that we have just created. Okay? Yeah? So far, so good? Song is asking here, could you please remind me how to restart Gazebo? I remember that there was an SH script. Yes. Let me remember this very quickly for anybody, okay? In case that anybody has some problems with the simulation or whatever, in order to restart the simulation, all you have to do is come here to the terminal where you have the simulation running, which is the first one, and here you press Ctrl+C. Okay, to stop the command. Okay? Now, even after stopping the command, you are going to see that the simulation still shows up here. Okay? So in order to fully kill and terminate the simulation, what you have to do is go inside the simulation workspace here, and here you are going to find an SH script, as somebody was saying in the chat, which is called gz_kill.sh. Yeah? So this SH script is used to fully kill the Gazebo simulation. Yeah? And you can execute it like this, gz_kill.sh. If you execute this SH script, this is going to completely terminate the Gazebo simulation, okay? And now, all you have to do is to execute again the previous command to start again the simulation, okay? So if you execute now again the command, this is going to start the simulation. There we go. All right? Is it clear? Yeah? Okay. Okay, so let's keep advancing. Let's keep advancing because we have many things to do yet. Okay, then we have created our package, right? Our pick and place package. Now, what we are going to do is to create our first version of the ROS2 program, yeah, to do the perception. Then here you have the program, yeah? It's a Python script, as you can see, and here you have the contents of the program, all right? So let's go ahead, all together. Let's go to the pick and place package, and inside the pick and place package, you are going to find another folder which is also named pick and place, right here. Inside this folder, you are going to see that there is an init.py file. So inside this folder, the second pick and place folder, we are going to create a new file, yeah? To do this, all you have to do is to right-click in the folder and select a new file, okay? And then we are going to create a new file which is named pick_and_place.py, okay? We create the file and the new file is going to appear here. Obviously, right now it's empty because we have just created the file, yeah? So next step is to copy the code from the notebook. So we select the code here from the notebook, we copy it, and we paste it here into the file using the code editor. Yeah, there we go. Okay. Now, let's continue by setting up our package, and then after that, I'm going to explain what's going on here in the program. Okay, but let's finish the setup first. So, second step is to update the setup.py file. Yeah, this setup.py file, you are going to find it again inside the pick and place package. At the very bottom, you are going to see here a file which is named setup.py. If you double click, you are going to see that it has some contents already, but you can just remove the contents and paste the ones here in the notebook. Okay? Yeah, there we go. And then basically we are editing this file just to add this line here, line number 23. Yeah, this is the important line because this line, what I'm doing is to generate an executable file from this Python script that I have created here. Yeah. And then last step is to compile and build our workspace, right? So in order to build, very important, we have to go to the root of the workspace. Yeah, right now we are in SRC, so we have to go to the root of the workspace, which is this folder, ROS2 workspace. Yeah, and here we can just run colcon build in order to build our workspace and build our program and so on. This is going to take a few seconds. Shouldn't take more than that. There we go. And then after building, very important to always source our workspace. Yeah, you have all the commands, all the code, everything. You have it in the notebook here. Yeah, so I'm just following the steps described here in the notebook. So final step is to source. And then now we are ready, as you can see, to execute our program. Okay? So actually, let's execute the program already. Yeah, so I'm going to execute the program here, and let's see what happens. Let's wait a few seconds, and you can see here some logs which are saying receiving video frame. And after some seconds, a new window is going to pop up, and you are going to start seeing here the camera view. Okay, so this is what the robot, what the camera of the robot is detecting right now. Yeah, so basically it's it's the front of the robot. Okay. Now let's have a look at the program. So what are we doing here? Okay, this is a very basic program, ROS2 program, which is creating a ROS2 subscriber, as you can see here. Yeah, so we are creating a subscriber for this topic, camera image row. This topic is the topic where the robot's camera is publishing all the images, all the video stream. Yeah, so everything that the camera is capturing it's publishing in this topic, camera image row. So in my program, what I am doing is to subscribe to this topic. Yeah. Then we are creating the CB bridge, which I'm not going to enter into details because we have already explained this in previous classes many times. Yeah. We create the CB bridge instance, and then using CB bridge, we convert the images. Yeah. Well, this is the subscriber callback. Yeah, the callback for my subscriber. So inside the callback, what I am doing here using the CB bridge instance is to convert the images from ROS message to CB2 message. Yeah, so that using the CB format, I'm going to be able to better process the image for perception and so on. Okay, and then finally, what I am doing is to display the image. yeah, with this IM show method. Yeah, so this is why I am capturing the images and I am displaying the images. This is why I can see this here when I run my program. Yeah? So far, so good. Is everybody following the class? Let me have a look here at the latest comments. Oh, Sajat was asking, what is the point of sourcing here? And Stefan has correctly answered, to update with the new package, pick and place. Yeah. Yes, yes, yes. Okay. So it seems everybody is able to follow the class so far. Bruce is saying, how can I use Sawyer or Fanuc robots instead of BotBox? Well, just, I mean, here we are working with a simulation. So in the same way that we are working with the BotBox simulation, you could load a simulation of another robot, a Fanuc robot, or a Universal Robots robot. Yeah, so any robot that you can have a simulation, you can do it, and also with the real robot. Okay, so let's keep going. Let's keep going. Now we have a basic program which allows us to have access to the data that the robot's camera is capturing, right? Now, the very first task that we would like to achieve is that we are able to detect these palette cubes, right? Then in order to do this, we are going to use the Aruco markers. Yeah? That I introduced at the beginning. Yeah, these patrons here, yeah, which are Aruco tags. Yeah, if you want to learn more about this, you can have a look, for instance, at the class 189, okay, which was perception with April tags for ROS 2. Okay, because here we go much more in detail about all this. Here I'm not going to get too much into details. Yeah, so basically these Aruco tags, Aruco markers, are 2D binary encoded fiducial patterns designed to be quickly located by computer vision systems. Yeah. So by performing a set of calculations using the patterns detected by the camera, these patterns, the robot is able to compute the 3D pose of the tag relative to the position of the robot. Yeah? So using these patterns, we can detect the position of the cube, the palette cube, with respect to the robot. Yeah? Which is crucial for our task, right? Then, in order to be able to perceive, to detect these Aruco markers, for this example, we are going to use the ROS2 Aruco package, yeah, which is this package that you can find here, yeah. Actually, there are some other packages like the interfaces and so on, yeah. And here in the notebook, you have a link to the open source repository here, in case that you want to learn more about this, the details of how it works, etc. Yeah, but it's very easy. It's very, very easy to set up. Okay, and this is very it's widely and extended in robotics because, as you can see, it's a system which is very easy to use. Right? You can print these patterns in a piece of paper and put it in any object. You can put it in a warehouse box, you can put it in a cup, you can put it in anything. And it's very easy to obtain, right? Just a pattern that you can print very easily and with a very low cost, right? So using this ROS2 Aruco package, we are going to detect this. We are going to try to detect this cube, all right? Then How does this work? Well, the details of how to use this package is explained here, but basically what we need to provide to the node, to the ROS2 Aruco program, is the topics where the camera is publishing, yeah? As you can see, this program needs to subscribe to the image raw topic, which we already know. It's this one here, right? Camera image raw. But in case that your camera publishes in a different topic, you have to tell this to the program, right? And also it needs to know the camera info topic, right? In order to get the metadata information of the camera. Yeah? In our case, by the way, also, if you run here a ROS2 topic list, you are going to see that we also have this camera info topic. Oh, actually, no. Let me run again. There you go. See, here we have also the camera info topic. Okay? Yeah? So, what are we going to do? Here we have some examples of how to run this step by step on commands. I'm going to launch. To jump directly to the launch file. Okay, so we are going to create a launch file in order to start two programs simultaneously. First is the pick and place program that we have created, and second is the ROS2 Aruco program. Yeah. Why? Because I want to run my program in order to display the camera feed, okay? And also I want to run, of course, the ROS2 Aruco node in order to be able to detect the Aruco markers, right? Then, let's create this launch file, okay? So for this, we are going to go again to our pick and place package in the code editor. And we are going to create here a new folder inside the package, yeah? So for this, you have to right-click on the package folder here and select the option New Folder. And we are going to create a new folder named Launch, okay? And then inside this launch folder, we are going to create our new launch file, which we are going to name pick and place.launch.py. There we go. Yeah, pick and place.launch.py. Okay, as you can see, sometimes when you create the file, it places the file anywhere in the package. See? So if this happens to you, just left click on the file and you can move it inside the launch folder, okay? So that we have the launch file inside the launch folder. Yeah, make sure to have it like this. We have to have the package organized, all right? And then we have one last step before executing our launch file, yeah? Which is to update again the setup.file, yeah? So we have to open again the setup.file. You can remove it. You can remove the contents if you want, and copy the new updated contents that you are going to find here in the notebook. Yeah? Copy and paste. Why are we updating this file? Well, it is because of this line number 15. In this line, we are telling our package that when we build this package, we are going to install in the system any file which is inside the launch folder and which has the extension .launch.py. Yeah? So basically, we are installing this pick and place launch.py file in the ROS2 workspace. Yeah? So, once we have done this, we are ready again to build. So let's rebuild our workspace with Qualcomm build. There we go. Okay, let's source after building. And now we can already execute our launch file with the following command: ROS to launch, pick and place.launch.file. Yeah? And remember, our launch file is going to, well, actually we have not filled the launch file yet. Okay, so I skipped the most important part. Let me go back up. And here you're going to find the contents of the launch file, yeah? So again, all you have to do is to just copy from the notebook and paste it here in the code editor, okay, like this. And as I was saying, this launch file is going to start two things: our pick and place program and the Aruco node, okay? Here we are specifying a parameter, which is the size of the marker. Yeah, and this is in meters, so this means basically 5 centimeters. Okay, these markers are of 5 centimeters. Yeah. Then, yeah, so I have to rebuild, sorry, because I have added the contents of the launch file, so I need to rebuild. Go. Okay, source. And now, yes, now we are ready to start our program with the following command. There we go. Okay, so we have started our ROS2 programs, launch file. So if we come here, we should see this, but apparently, nothing strange is happening, right? Now, let's analyze a little bit more what's going on here, okay? Because we are running our Aruco program, right? We have started our Aruco node here. So let's open another terminal here, a third terminal, okay? And here we can, for instance, run a ROS2 topic list, and we are going to find a couple of new topics here: Aruco markers and Aruco poses, okay? This is very important. Why? Because as we are explaining here, the Aruco node, yeah, this Aruco node, whenever it does a detection, it's going to publish the detection in the Aruco markers topic, yeah? So any detection that is made by the ROS2 Aruco node is going to be published into the Aruco markers topic, yeah? So this means that if I subscribe to this Aruco markers topic, I should be able to get any detections made by my program, right? Now, I am not getting any detection. Why is that? Can somebody tell me why I am not getting any detection here? Anyone? Vivian says, camera sees no Aruco marker. Very good. That's totally true, Vivian. Exactly. So I don't have any detection because the camera is not seeing any Aruco marker, right? Then it makes sense. So let's do something. Let's move the robot so that the camera can see an Aruco marker, okay? Then for this, we are going to use our beloved teleop program. I don't know where we have, I think it's up here. Yeah, here you have the command to launch the teleop to his keyboard, yeah? So that you can command the robot with the keyboard, yeah? So let's open the fourth terminal here, because here we are going to run the teleop twist keyboard program. Yeah. So let me copy here and paste. And then now let me rotate the robot so that it faces this Aruko marker here. Yeah, so let me rotate the robot a little bit to the left. There we go. Okay. Let's stop here. Okay, so here, all right, there you go. Yeah, so here, if I open the camera, okay, there we go. So now the camera is seeing an Aruko marker. So what if I check again the topic? Okay, so now I can see the Aruko detection being published here in the Aruko marker topic. Yeah? And we can even see the position of the Aruko marker with respect to the robot. Yeah? Which is basically, as you can see here, 10 centimeters in the x-axis and like 8 centimeters displaced in the y-axis. This is with reference to base link, okay, which is the base of the robot. Yeah? So far, so good. Let me stop all this now. Let me stop all this. Yeah? Has everybody been able to reproduce this? Franco was suggesting maybe Aruko program is not connected to the right topic. That is a very good suggestion, Franco, actually, okay? In this case, it's not the problem because we were connected to the right topic, but that is something that happens very, very often, okay? That you are running a program, but you are not configuring the program to connect to the correct topic. Yeah, this is very, very typical, very, very common error in robotics. So that's a very good suggestion. Its coordinates are XYZ, Franco. I can see some comments here. Okay, I can see that there are being some side conversations here, but I will let you talk on your own. Then, have you been able to reproduce this example that I have just shown here? Yeah? To launch the program and get the detection in the Aruko markers topic? Yes, no? Anybody has been able to have this example working? Yes, yes. Fayez is still working on it. Okay, so don't worry, Fayez. You can go at your own pace, but I can see that most of you have been able to complete this. So let's keep advancing, okay? This is the first step. We are able to use the ROS to Aruko packages in order to detect the Aruko marker, okay? So now we are going to go a step further and we are going to mark this detection, okay? Not mark, but we are going to show this detection so that it is very clear in the display, okay, basically. Then, in order to do this, what we are going to do is, first of all, we need to subscribe to the Aruko markers topic. Second, add a callback function that will take the pose information that we need and store this information into the class. Third, use OpenCV to display the tag ID, the position, and the position of the marker. Yes, so the tag ID of the marker and the position of the marker. 4, Draw a circle around the center of the detected tag. 5. Draw a line from our current position to the center of the tag. So draw a line from the robot to the detection, to the detected tag, right? And finally, determine the angle from our current position to the tag using the orientation information from the tag. Okay? So as you can see, in the information of the detection, we have the position, but also the orientation. Yeah, the orientation in this case, this is in quaternion. Okay? But we are going to convert it to degrees and so on. Then we need to do all this. Okay? So how can we do all this? Well, here we have all the code. Yeah? Explain it step by step. What I'm going to do is to copy directly the new version of the code, updated version of the code. I'm going to copy it, and all of you, please do the same. Copy the updated version of the code that you are going to find here, and replace it by the old one, which is here. Yeah, so let me remove this and paste the new code. And now we are going to have a quick look at what we are doing here. Yeah, before we run it. Okay, so we have our subscription to the camera topic, and also now we are subscribing to the Aruco markers topic. Okay? Then, in the camera callback, which is this image callback, we are looking for markers. Okay? Here we have a for loop where we are looking for any marker in this self markers list, which we have defined up here. Okay? So we are going to iterate over any marker detection. And we are going to extract some information from each detection, like the marker ID, the position, and the orientation. Okay? Then we are going to convert the position information to pixel coordinates. We draw a circle at the marker position using the CV2 circle method. This we have already seen also in previous classes. We draw a line from the center bottom of the robot, so from the base link of the robot, basically, let's say, to the marker position. Yeah? Actually, this is the center bottom of the image, which represents the center of our robot, the base link of our robot. Yeah? And then we calculate the angle in degrees from the orientation. Yeah, so you can see here we are doing some operations to transform from quaternion to Euler angles. But basically all this is to get the orientation of the detection in degrees. And then finally here we are drawing some information in the display. Okay? And finally, in the second subscription, which is the subscription to the Aruco markers topic, we have its corresponding marker callback, and here what we are doing basically is to do the detections. And any detection that we do, we are going to append it to the self markers. Yeah? So that we can then later analyze it and process it here. Yeah? So what is the final result of all this? Okay, let's have a look. Let's compile all this. Let's go back to our workspace. Let's rebuild the package. There we go. Let me source. And let me run my program again. There you go. So let's see what is the final result of all this. Okay, There we go. So this is the final result, okay? We can see here the detection, which by the way, it's a bit displaced. Let me move a little bit the robot around to see if I can correct it actually a little bit. Let me rotate there. Okay, see, so if you rotate the robot, you should see also how the point and the line change and get updated. Okay? Yeah, so the program is not perfect. It can be improved, of course, yeah. But at the end, you should see something like this, yeah? So we have the camera view, and then we have some information related to the detection. We can see here a circle, which is drawn in the detection. We have a line which goes from our robot to the detection, and here also you can see some information like the tag ID, which is 5, and the information of the position and orientation in degrees. Okay, very important, so that I can now create a controller to move towards the detection. Yeah? Does it make sense? Do you understand everything that's going on here? All this information that we are printing here? Any good resource to understand quaternions better? That's a very good question, Sajat. I don't know. Right now, I don't know. But quaternions, it's a pretty complex thing to understand. But I'm sure that if you look around, you are going to find several resources, but I cannot tell you one specific right now, because I don't know. But yeah, that's a very good question, actually, because quaternions are a bit tricky. This is why always, or usually in robotics, what we do is just to convert it's to convert the information from quaternion to Euler. See, like we are doing here. This function that we are using here is basically to convert from quaternion to Eulers, because we always prefer to work with Eulers. It's much more intuitive. Yeah, that would be an interesting open class for sure. Yeah. Okay, so I can see that everybody is clear so far. Then let's keep advancing, because we are already quite late in the schedule. Already past 1 hour. So let's try to finish the first approach of our program. Yeah. So what is the current status? The current status is that we have a program which is able to detect the Aruco marker and display some visual information about the detection. Okay, this is just visual information. Yeah, so that it is more clear here what is going on. Yeah, then what is the next step? The next step is going to be to use this detection in order to pick the pallet cube. Okay, now for this, we are going to do a couple of things. First of all, we have to use the action server that we have seen previously, the gripper controller action server that we saw at the beginning. Yeah, we did some tests here in order to open and close the gripper. So we are going to connect from our program to this action server in order to be able to control the gripper, to open and close the gripper, right? First thing is to do this. We need to add this to our program. Second thing is that we are going to add some kind of control system, some type of controller, in this case a proportional controller, in order to move the robot towards the detected Aruco marker. Yeah, with the information that we have of the position and orientation of the detection, right? So we need to do these two things, okay? By the way, here you have some more a graph showing an action server. Even here also, we have added a video which is dedicated to ROS2 action servers, how to create an action server, etc. Okay, so in case that you are not familiar with action servers, you have some additional information here. All right? Now, let me actually go for it, yeah? So here you can see the new additions to our program. So we are going to create an action client to connect to the gripper controller. We are going to create a publisher to send velocities to the robot, to the command belt topic, yeah? You are already familiar with this. We have some helper attributes of the class to detect, or to, not to detect, but to say when the gripper is open and closed. And then here we are going to build a controller, as you can see, in order to move towards the detection. Yeah? So this is a simple proportional controller, simple proportional algorithm, based on the offset of the robot from the center of the tag. Yeah? So based on the offset of the robot here from the center of the tag, this offset here, we are going to send the velocities to the robot, okay, in order to correct this error. Yeah? Then here you have the final version of the program, okay? So let's actually copy all this program, and we are going to have a quick look at it right now. Then one more time, let's come to our pick and place program and remove the code and paste the final updated version. Yeah? Then let's have a last look at the program to see what we have here. Quick overview, yeah? So we have the camera subscriber, we have the Aruco marker subscriber, we have a publisher to send velocities to the robot, and we have an action client to connect to the gripper controller, yeah? Some attributes, helper attributes. Here we have a new method, which is to send a goal to the action server. Yeah, here we are going to send a goal to the action server, whether if it's to open or to close the gripper. Yeah, so we are going to use this function for this, for opening and closing the gripper. Then here we have the image callback, where we have already seen previously what we were doing, but now here we are adding some checks, for instance, to open the gripper. Yeah? So if there is a detection if there is a marker detected, then we are going to open the gripper. Yeah? And this is the same version as we had before, where we are getting some information for each marker detected, such as the ID, the position, and the orientation. And then we print this information, yeah, in the camera view. And then here also we have the proportional controller part, yeah? So we are calculating the offset here from the center of the image to the detection, yeah, to the detection of the marker, and we are using this offset in order to rotate the robot so that we can align the robot with the detection, okay? And then finally, we publish the velocity, the final resulting velocity to the robot, okay? This is the marker callback, where we are doing the detections of the markers, and basically that's it. Yeah, so we have changed it a little bit, as you can see here, the image callback, in order to add instructions to open and close the gripper, and to move the robot towards the detected Aruco marker, okay? So, let's execute our program. Well, first of all, of course, we need to build. Let's rebuild our workspace. There we go. Then let's source. And let's execute again our program. ROS to launch. Okay, and let me open the camera so that I can see what's going on here. Let's put also this here. Okay, so there we have the camera view with the detection being made. And as you can see here in the simulation, the robot is already moving towards the detection. Okay, so you can see now it's the robot is rotating a little bit to the right in order to align and to correct this error here. Yeah. There we can see that it's rotating a little bit, it's very slowly. It's moving towards the tag. So let's see. We can see here again the detection, which is very cool. The line with which aligns the base of our robot with the detection. And the robot here, which is moving towards the detection, while it tries to correct this offset. Yeah? Of course, this program can be improved in many ways. Yeah, but this is just a basic program to demonstrate all these things combined. All right? Now, right now, the gripper is opened, as you can see, but there is a logic in order to close the gripper. I will show it to you in a moment. So basically, the logic is that whenever there is a marker detected, we open the gripper. If there is no marker detected, then we close the gripper. Okay? So if the robot keeps advancing, at some point it's going to lose the detection of the marker, right? Because it's going to, the marker is going to be out of the camera point of view, right? Then at that point is when we are going to close the gripper. And we ideally should pick the cube. Okay, we are going to see that in a moment. We are almost there. Let's see. Okay. Okay, we are going there. For some reason, the program is moving to the robot is moving to the right when it should be moving to the left. Here. Yeah, it's because this circle is not being printed correctly. Okay, let me stop. Let me actually stop the program here and try to... I'm going to help it a little bit. Let me go here. Yeah. Let me try to rerun the program here from this point. Okay. For some reason, the controller is not working as it should. Okay, let me do one thing. Let me try to reset the simulation and everything, just so that I have something which is working fresh. Okay. Let me do this very quickly. GZ kill. Sorry. Okay, relaunch the simulation. And just to speed things a bit up, I'm going to help the robot. No. I don't want this view. I want the other one. What about you? Have you been able to have it properly working? Because I know it works, okay? Probably it doesn't work 100% of the times because, as I was saying, it's just a test program, but it should work pretty well. So probably some of you manage it to have it working. Okay. Okay, yeah, sorry. Let me run out the simulation. All right, there we go. Let's zoom a little bit. And let me rotate also a little bit the robot here to the left. Actually, this is not needed because if there is no detection, the robot is going to automatically rotate to the, it should rotate to the left automatically because of how the program is created. But yeah, let's help it here a little bit just to speed things up. And let's give it a second try. And okay, there we go. Let me have a quick look at the chat. And that would be a great open class. Juan has shared here a resource for the quaternions, which might be interesting. The gripper seems to be touching the tag and therefore not progressing. Yeah, it works good for me, says Stefan. Yeah, I mean the program is very basic, so it can be improved in many different ways, just so that it's more robust. Okay, but yeah, basically, yeah, there are some problems here that with the detection also, which is not being exactly placed in the center always, and there are some issues there. But yeah, let's see if we have it working properly this time. Actually, that's something that you should do, all right, to improve the code so that it is much more robust. Okay, that is something that you could perfectly do for homework. Yeah, so here the program should be rotating a little bit more to the right, and it's not. Yeah. Which probably that can cause some problems, but well, we'll see. Okay. Okay, hopefully here, oh, now it's pushing it after the, okay. Okay, now I think it's going to do it. Yeah, because now it's going to stop detecting it. Right, there we go. At some point, it's going to stop detecting it, and then it's going to close. Yeah. Okay. So here, ideally, let me stop the program already. So here, if I move back, yeah, I have the cube picket. Okay. Whoop, there we go. All right. All right, so here you can see it more or less working, okay? Then I'm going to already leave it here, already 20 minutes past the finishing time of the usual finishing time of the class. I'm going to leave it here, and then I'm going to send to you as challenge and as a homework a couple of things. First is to improve this detection program, okay? So that the detection and the approach and the peak of the pallet cube is much more smoother and robust. And second, once you have the cube picket, yeah, you should be able to autonomously be able to move to move the robot around the environment and send the pallet cube to another place in the warehouse. Okay? Yeah? For instance, a method that you could use could be to use line detection. Okay? Just a suggestion. But yeah, I'm going to leave it here. Let me. Gripper seems not wide enough, so sometimes got stuck. Yeah, probably that's an issue, but you should be able to do it. You should be able to do it properly, even with this opening of the gripper. Okay, just by adjusting a little bit more especially the final approach to the pallet cube. All right. Can we run the same code on ROS to Foxy instead of ROS Humble? I don't know, Krishna. All this has been tested in Humble, so it's very likely that you are going to have some issues if you try to run it directly in Foxy. Okay. In any case, you can try it, and if you have some issues, you can just fix them and do small adaptations. Yeah. To port this program to Foxy. Okay? It shouldn't be too difficult to port it from Humble to Foxy. Okay? And maybe even it works on the first try. So you could try it, Krishna. All right. So I'm going to leave it here then. Thanks all of you for attending this class. I hope that you enjoyed it. I hope that you have learned something new, and I hope that you stay here for next open classes. We had many new students today, first timers, so I hope that you liked it, that you had a good time, that you learned, and that you stay with us for following open classes. And yeah, I'm going to leave it here. Thanks again. See you in the next one, and as always, keep pushing your robotics learning. Bye bye.